Hey there, awesome physics students. I wanted to do an example with adding vectors with components. This is complementary to the tip-to-tail method. This is a two-dimensional example. I have two vectors, A that has a length of 10 meters or magnitude of 10 meters at an angle of 30 degrees to the horizontal, and vector B, which has a magnitude of 8 meters at a 60 degrees to the vertical. And you notice that B has a negative x component, so we're going to have to take that into account. Okay. The first step in doing this, of course, beyond drawing the vectors, is to find the components of each vector. So we want to find AX and AY first, so let's go ahead and get started. So I want to find the right triangle here, and that right triangle is going to be like that. And if I, so AY is going to be the component over there in that direction, the y direction, and then AX is going to be the component along the x-axis, like that. To find AX, notice that AX is adjacent to the angle 30 degrees, and so I'm going to use cosine for that because cosine includes the adjacent part. So that's going to be the hypotenuse, 10 meters, times cosine of 30 degrees. And when I punch that into my calculator, I get 8.67 meters, and that is positive because it points in the positive x direction. Okay, I have to check that each time. For AY is opposite of the 30-degree angle, so I need to use sine for that. And so I take the hypotenuse and multiply by sine of 30 degrees. And when I punch that into my calculator, I get 5 meters. And again, that one is in the positive y direction, so I need to check that every single time. Let's find BX and BY. So for the right triangle, there's a couple of them you could find here. Let's try this one to start with. And so this is the part of, here's another triangle you could find. This part along this x-axis, that's BX. Let's use this upper one though here because it's the same one, but it's a little more convenient. Notice that that is opposite of the angle 60 degrees, so I need to use sine because that includes the opposite side. So I take the hypotenuse, 8 meters, and multiply by sine of 60 degrees. And notice that that is, when I punch that in my calculator, I get 6.93 meters. But notice that this is in the negative x direction, and there's nothing about what I've written here that will indicate that it's a negative number, so I have to put the negative number by hand. Okay, so that is a negative 6.93. For the y component, that's going to be this side right here, which is also this side here. I'll write it over here for convenience, a little more space over there. And that is going to be, that side, of course, is adjacent to the 60 degrees. And so I need to use cosine for that. So I take the hypotenuse of 8 meters and multiply by cosine of 60 degrees. And when I punch that into my calculator, I get, that gives me 4 meters. Okay, so this side is 4 meters. All right. Now that I have all my components, I can write the equation here. The equation is going to be that the vector r, and I'm just using r for the resultant, is equal to the vector A plus vector B. And this tells you that r, the x component of r, is equal to AX plus BX. And keep in mind, AX and BX, you always add them, but internally BX, we know that that is a negative number, so we're really subtracting two numbers here. And then ry is equal to AY plus BY, and of course in this case they're both positive. Okay, so we need to find those two, and once we find those two, we know everything there is to know about Rx, about the resultant vector R. Okay, so let's start with Rx. So Rx is equal to AX, which we decided was 8.67 meters, and that's positive. And BX is negative 6.93, and we add those two. And that when we add those two numbers, we get a positive 1.74 meters. And then for ry, we do the same thing. We take 5 meters plus 4 meters. And that, of course, gives us 9 meters. So now that we know this, we know each of the components of r, we know what r is. Okay? And we could write r as, using our trig functions, we could write r as a magnitude with a direction angle if we wanted to at this point, but we have all the information needed to do that. Another quick note here, to connect this with the tip to tail method, you could take this b and move it over here, and so you could write b like this. And remember, if we were to shine a flashlight down here, then the resultant would cast a shadow along this axis here that we would want to be sensible. And so if I do that, the resultant, of course, goes from where you begin to where you end there. And so the resultant looks like that. And apologize for this mess, but that's just the way it is with these diagrams. Sometimes they get really busy. If I were to shine my flashlight down, should probably move the flashlight over here. And the resultant, the length of the resultant here is going to be right here. And it makes sense that that is only 1.74 meters. And then the length of the resultant in the y is 9 meters. That's along this axis. So you can see that's going to be this 5 meters plus 4 more meters here. And for the x direction, it is 8.67 out here, but then I go backwards 6.93, and that takes me to a total of 1.74. Okay, so this shows you that the tip to tail method and the component method are totally consistent. Much of the time, we are going to prefer to use the component method, okay, just because it's, for computations, it's much more effective and gets you the numbers you want. For concept, though, the tip-to-tail method is actually much more useful if you want to figure out the direction of an acceleration, for example. All right?